Okay, students, we have a pretty important lecture today. We're going to work through the concept of energy, which we alluded to at the tail end of Thursday's lecture. And we're going to have some homework tonight due on Thursday involving the concept of energy. We'll go through some examples with it in lecture today. So be ready to take good, careful notes. As an additional comment before we get to that, let me remind you of something that I mentioned in web courses, and I'll mention it directly now to you face to face. And that is, I've shifted our office hours. They were 10:30 to 11:30 on Wednesdays, but I've shifted them to 10 o'clock to 11 o'clock. All right? Now, I haven't had anybody come, so I'm not sure if that affects, not a single one of yous. Although I had some students come last week, but I had to leave to go to the dentist last week. But hopefully some of you will be able to come to those. Also, Miss Darian has office hours 11 to noon this Friday, and we're thinking about modifying or adding to that. We have an exam next Tuesday. So the lecture today on energy and then the thermal energy concepts that we get to on Thursday this week will be on exam number 2 on Tuesday next week. And then on Thursday next week, we'll get down to some, oh, you know what? I take that back. We're going to do angular momentum. So we're going to do angular momentum chapter 5 on Thursday this week. And maybe we won't get to all of chapter 5, but we'll try to get to most of chapter 5 Thursday this week. And then after the exam on Tuesday, we'll finish chapter 5 and then get into thermal energy concepts next Thursday. So that's just kind of a little blurb or discussion of coming attractions. Questions here in front?
Was the exam date moved? Because when I last checked, it was like the 6th.
Wait a minute. The exam date is, yeah, that's the 6th next Tuesday. Oh, wait a minute. So that's right. It's Thursday. It's Thursday the 8th, right? Oh my goodness. Yeah, okay. So, okay, take back everything I just said about the exam next week. So we'll actually have Tuesday lecture. And then Thursday exam. So sorry about that. I was, you know why? Because I've been doing Tuesday exams up to now. This is the first, and I think it's the only Thursday exam, right? Yeah. Is that correct? Okay. The final. Yeah, and then the final. Yeah. So, okay. Thanks for. Is that what you other guys were going to say with comments over here? Okay. Yeah. So Thursday next week, so we will probably get definitely all of chapter 5, and then on into thermal energy a little bit. And then Thursday next week we'll have that quiz, right? And then I'll give you guys the week after that off. All right? So I'll just give that, that whole week. Okay? Because you know where I'm going to be going for my, spring break? I'm going to Ohio. Isn't that thrilling? Who's going to Cancun? Anybody? Yay. Who's, we're already in Florida, so I guess most of you guys are going to go to the beach. Anyways, have a great, I hope everybody has a good spring break. I'll be going up to Ohio. Now, let's get your clickers ready. We're going to do some clicking and clacking. We're going to use some, your brain is going to start clicking and clacking. And hopefully you'll start getting your mind ready. Our big target by the end of the semester, the end of April, is understanding things about molecules and atoms and how they form. And one of the molecules I'm going to talk about today is retinal. And retinal is an important molecule. It is the molecule that responds to light in the retina of your eye. It's part of the rhodopsin molecule. And rhodopsin, retinal is the part that actually responds to the incoming photon of light. So if you have a red, an orange, a yellow, green, blue, indigo, or violet colored photon of light, a particle, a quantum of light, it'll interact with this molecule. The molecule will, it'll move in a very particular way. And when that happens, your optic nerve fires. You get a signal proceeding up to your optic nerve and into your brain, to the part of your brain that processes images, which is for us phenomenal, for humans especially, phenomenally powerful. It's the most powerful, I don't know, I would say it's the most powerful part of your brain, but somebody else might differ with that. So we're going to talk about retinal, the special molecule, but let's get down to business with the mass unit that is conveniently sized for atoms and molecules, and that's the atomic mass unit, AMU. And some places you see it listed as U, the unit, U for atomic mass unit, all right? And you see it listed implicitly in the periodic table. Like here's a little tile of the periodic table for oxygen, okay? And that number down at the bottom, 15.99, is a reflection of the mass of the oxygen atom. So let's get down to basics, okay? And we don't use kilograms and grams, although we could. Instead, we use the atomic mass unit. And basically, the atomic mass unit is, pretty close to the weight or the mass of a proton. And the formal definition is, for the atomic mass unit, for the most abundant form of carbon, called carbon-16. And most of the carbon in our planet is carbon-16. And all the limestone that we have, most of it's carbon-16. The atomic mass unit is defined as 1/16 of that common form of carbon mass, all right? And so basically it works out to about the mass of a proton. So the hydrogen atom is pretty close to 1.0 AMU, because that's all it is. Now, side note, you might be thinking to yourself, hey, Dr. B, isn't there an electron inside a hydrogen atom? I mean, a neutral hydrogen atom? And the answer to that is yes, but the mass of the electron is really, really small. It's about 2,000 times smaller than the mass of the proton, and the neutron is about the same size as the proton. So electrons, yeah, they're in there, but they don't really affect many of the digits until you go out a few more digits. So hydrogen, yeah, about 1.0. Oxygen, 16, which is reflected in this little piece of the periodic table, 15.99. All right. And retinal is about 284. So write down the mass of the retinal, because you're going to be doing a calculation of momentum for retinal in just a second. All right. And this is a realistic calculation. So 284 AMUs. So that's like saying you have so many kilograms, But with kilograms, you'd have to use the big scientific notation and stuff. But this is easier, just 284 itty-bitty AMUs. All right, so for instance, if you have an object, an atom or a molecule moving at 1.0 meters per second, then you just multiply that by how many AMUs. All right, and that would be, for hydrogen, moving at 1.0 meter per second, its momentum would be 1.00 AMU meter per second. So it's kind of like, you could state it in kilogram meters per second. There it is, over there on the left side of the screen in that red outlined box. But that's a whole lot of digits. And 1.00 AMU meter per second is perfectly fine. And when you're working with atoms and molecules and stuff, it's sometimes a lot easier to stay in these units. Although you can, eventually you might want to convert to kilograms or grams. But yeah, this one's fine. They're equivalent, all right, in terms of momentum. Now, similarly, an oxygen atom at 1 meter per second is going to be about 16.0 AMU meter per second. All right, so whatever, take that number up there for hydrogen, multiply it by 16, and that's how much the oxygen has for momentum in these kind of weird molecular units. Right? And then, now here's the one that we really want to focus on. The momentum of the retinal, if it's going 1.0 meters per second, between here and Miami, it would have a momentum of 284 AMU meters per second. Now, I think I'll give you a molecule problem in homework. Wait a minute. Did that hexagonal molecule problem, was that in AMUs? No? Was it AMUs? Okay, so molecular mass units. Okay, MMUs. Well, I should have made it AMUs. Anyways, I'll probably write a new problem for you for tonight's homework in AMU meters per second, just so you have a little extra practice. All right, now I want you to give a calculation. We're going to try a calculation with retinal. It's going to be multiple choice. And here's what we're going to do. What we're going to do is we're going to slam a photon into the retinal molecule. And the photon is going to give up all of its momentum to the retinal. So it's like a boxcar that disappears. That's a cool way of thinking about a photon, actually. Because a photon does not have any mass. It transfers its energy into the retinal molecule, and there's no longer a photon. The energy of it is in the retinal molecule. So here we go. A photon delivers a delta P of 71.0 AMU meters per second. And jot this down in your notes. It's a good calculation to have on the back burner. And think, the only difference here is it's like boxcars. I posted a discussion thread a couple days ago that the green hex protein problem was just like boxcars, except it's molecules. But now this one is like boxcars, where the moving boxcar has momentum, but no mass. So it transfers all of its momentum, but it doesn't add anything to the mass. So you can't go, divide by 4. But you can still use the same concepts, conservation of momentum, Definition of momentum. How many have we got here? So, consult with your neighbor, talk it over. If nobody's sitting in your role, you'll have to use your mental power and superior strategy. You know what, Darian? I wish I could go to Chick-fil-A and get a sandwich right
Just go.
now. Nice.
Leave this open until you get back. It'll be fine.
P equals MV. Yeah. P equals MV. See, this is good. That's good. Well, yeah. No, not yet.
I know not yet.
Yeah.
So when you're ready.
All right, 30 seconds. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, my wonderful students, let's take a look at the results here. Okay, you can see that there's no clear winner. Option B is correct, and that got the biggest group, but not a majority, 35%. So let's talk it over. All right, go back to the regular. All right, here's your answer. Now, let me re-emphasize as you take notes here, the photon is massless. It's an object that has energy and momentum, but no mass. And that may seem strange to you, and it is strange, but that's the way that the world is set up. Its momentum is absorbed by the retinal, but the retinal does not acquire any additional mass. So the mass of the retinal is now 284 as before, but now it's got some delta P. All right? Now, as you can see in the statement of the problem, the retinal molecule, in this example, kind of idealized, is at rest in the retina of your eye. So that means that the initial momentum is 0. So let's figure out delta P first. Here we go. Delta P, by definition of delta P, is PF minus PI. All right? Now, PF, we don't know that quite yet, but we know PI, that's 0.0 AMU meters per second, all right? Because it's at rest. Now, we also know that this photon delivers 71 AMU meters per second. So all this junk over here is equal to 71.0. And so what that means is that PF, after the collision, the momentum of retinal after the collision, is 71.0. Right? Now the photon has lost all of its momentum. It's completely absorbed, like an amoeba. And now the 71 AMU meters per second that the photon used to have. Now the retinal's got it. This is how interactions proceed on the molecular level. And this is kind of simplified. You know, there's all kinds of things happening. All right, so PF is equal to 71.0 AMU meters per second, because that's, you know, what the photon had, the retinal now has. All right, now, according to the definition of momentum, P equals mv. That's, you know, nothing bodacious there. That's what this is right here. So here's mv, and I've got it denoted vf for v final of the retinal. The v initial was 0 because it was at rest, the retinal. Okay, and now this is where it's a little different from the boxcars, because in the boxcar type problem, you go from like 3 boxcars to 4 boxcars. Okay, or 4 boxcars to 5 boxcars, because one of them, in my patented boxcar problem, one slams into 3, one slams into 2, one slams into 4, etc., etc. This one, the boxcar slams in, it gives us some momentum, but no mass, right? Which is kosher for atoms and stuff. So really your deal here is 71.0 AMU meters per second on the left, and then 284 AMUs times whatever the new speed is, and that's what we want to figure out, all right? So V subscript F is this quotient, 71.0 AMU meters per second in the numerator. And so this is like the box. I mean, we're doing boxcar technology all through here. You know, momentum. This is basically collision technology here. All right. And 284 AMUs in the denominator. Yeah.
I made some mistake because the photon has 0 mass, so when I did the formula, I did 0 times 71.
Yeah, 0 times 70. Yeah. See, I phrased this. I didn't give you, what's the speed of the photon? Speed of light. So you know what changes with the, I'll give you guys a little sneak peek deep into the heart of quantum physics. The thing that changes, all photons go at the speed of light, but they don't have any mass. So MV doesn't work for photons. You know what changes as the momentum changes? The color. The color of the photon. So a photon that you would see as red has a little bit less momentum than a photon that you would see as blue. You know, blue is higher energy, violet even higher. Ultraviolet photons, really high energy. You know, so high energy they'll give you sunburn, skin cancer. X-ray photons, really, they'll penetrate bones. No, they'll penetrate your skin, but not bones. You know. Infrared photons, they're so deep red, you can't even see it. But less momentum than a red photon. So it's kind of, you know, light is a lot of cool things about light. And we're going to be getting to that, as I said, towards the end of the semester. All right, you can cancel the AMUs. Cancel them up there in the second equation block if you like, or cancel them down here in the quotient, either place. And what you're left with is meters per second of speed. The AMUs are out of here. And so you have 0.250 meters per second. All right. So I might put another photon problem. Maybe something with sulfuric acid. Maybe that would be good. Or maybe something, well, DNA is too big. What was that? What? DNA. DNA is too... What happened to my mic? Anyways, I'll give you a good molecule tonight for your homework. All right, so that's a little bit of mass, AMU mass, and just applying simple collision concepts with molecules. Now, I want to get back to this idea of space-time. Last time we talked about coordinates and dimensions in space-time. Just like Dr. What is that guy's name? Dr. Who? Time and relative dimensions in space. All right, so what we normally do is we construct a coordinate system in order to diagram and calculate distances, curvatures, et cetera, for various events. Okay? Now, I use the word event because, you know, an event is something that happens on a calendar. And so if you are thinking about time, you have to include the time and the location. That makes it an event. So usually we use rectangular coordinates, x, y, and z, you know, but they could be spherical coordinates, you know, latitude, longitude, and distance from the center of the Earth, or some other kind of curvilinear. There's all kinds of weird curvilinear coordinate systems, you know, like elliptical coordinates. You know, sometimes you want to use those, but we're going to stick to rectangular. Now, Einstein says that we must use time as more than just a bookkeeping device for calendars and checkbooks and stuff, which, you know, basically that's what Sir Isaac Newton's idea was. You know, that if you know, Sir Isaac Newton thought that time flowed the same way everywhere in space, everywhere in the universe. And Einstein said, maybe not. So if you consider time as a fourth dimension, then you have to think about the universe itself as a space-time, a four-dimensional space-time. And so what we'll do is we'll try to treat time as much as possible the way that we treat x's, y's, and z's. So meter sticks for x's, y's, and z's, clocks for time. And here's the correspondence that we talked about last time. And it is simply that if you think about time as the first of four dimensions, then the dynamical quantities are encoded similar. And you know what? The cool thing about photons, there's a very simple formula for this vector, energy and then momentum, px, py, pz, for photons. And that's exactly where you see the changes in the colors of photons with momentum. Anyways, so that's the correspondence. So what, you know, so Einstein's saying, don't think, you know, don't forget F equals ma. But if you're working in space-time, all four dimensions, think primarily in terms of energy and momentum. All right? And energy is what we're going to take a look at today. It is the dynamical quantity that encodes changing speed. Now, what does momentum quantify? Well, momentum encodes speed and dimension, the quantity of motion as a vector, as a spatial vector. But energy encodes things a little bit differently. And because it's the partner, it's the space-time partner of time, not of space. So let's take a look at it. So we're in chapter 4, and we're diving deep now into chapter 4. And what I want you to think about is the trajectory of an object through space. You know, something that we've talked about, you know, we've talked about left and right. We've talked about a baseball arcing up, you know, or a straight pop-up fly, and all kinds of stuff like that, the path. And an object that's on a curved path is going to have some accelerations, and it's going to have some net force. So the question is is the force tangent to the path or is it perpendicular to the path? All right? Or is there a little bit of each? So tangent to the path means this. If it's tangent to the velocity, parallel to the velocity, so wherever this thing's going, the net force is in the same direction as the velocity. So that's like in straight down free fall. In free fall, like an apple or an army man jumping out of an airplane. Actually, an army man jumping out of a helicopter with a parachute, free falling straight down. His velocity is downward. The apple velocity is downward. And so is the net force, mg. That's downward. And hey, you guys, we're going to start using negative 9.8 meters per second squared today in our equations because the downward versus upward motion is something we got to keep careful track of. This thing's fading in and out. Now the other option, if you're tangent to the path, the force could be anti-parallel to the velocity. So for free fall, that means that it's like a pop-up going straight up. Okay, a pop-up, the velocity is straight up in the air, but the gravitational force is straight down. So that's anti-parallel. Okay, you're 180 degrees away from the direction of your velocity. Okay, so Vanessa, when you have something anti-parallel, a force anti-parallel to the velocity, what happens? You slow down. Okay, so the speed is changed. So the relationship of the net force to the tangent of the path is related to changing speed. Let me repeat that because it's important. You know, there's two different kinds of tangent. Parallel, same direction, free fall downwards, and you gain speed downwards. So the speed is changing, and that's what energy encodes. Right? Anti-parallel, A2. You're moving up, a pop fly moving straight up, or you jump up. You know, you're on a trampoline, you jump up. But the gravitational force is straight down. That's anti-parallel, opposite directions. And you slow down. You know, you're on the trampoline. You don't keep going out into space. You rise to a certain level above the trampoline. You stop and you start coming back down again. All right. So all that, this geometric relationship between the velocity vector and the net force vector, parallel or anti-parallel, has a profound change on the speed. Now, what if the force is perpendicular to the path? If it's perpendicular to the path, right angles to the velocity, what changes? Not the speed, what changes? The net force is perpendicular to the velocity. What changes? Not the speed, what changes? The direction, that's right. All right, so now, that relationship is not something that we're going to build into the energy concept. I mean, we're going to be aware of it, but we're going to know that if there's a force perpendicular to the path, that force, whether it's 1 Newton or 2,000 newtons or 78 times 10 to the 23 newtons, it's not going to change the speed. It might change the direction. That's nice, but it's not going to change the speed. Okay? And energy encodes the speed, but not the direction. Momentum is encoded with direction, but not energy. So every path, now here's the other thing that we want to do. We want to think about every path. It can be measured out in segments. All right? Now there's a couple ways to do that. You know, if you think about a path as segmented out in equal, you know, like out on the highway you have mile markers. Okay, that's a spatial segmentation of the highway. But you could easily do, you know, if everybody was traveling at the same time, You can have temporal mile markers. Okay? So you could use delta t, you know, sequence of clock measurements, T2, T3, and on up to T subscript n, you know. You know, for some path that goes from A to B, you know, from point A to point B. You know, Orlando, the Turkey Neck Service Plaza down to Yeehaw Junction, right? That's a segment of the turnpike, you know. And the other way is just, you know, the conventional way, conventional for the highway department, and that's mile markers, okay, or meter sticks, delta S. Now, delta S here is my generic symbol for delta X, delta Y, or delta Z, or any kind of spatial coordinate. So delta S is just some kind of spatial coordinate. So S1, S2, S3. So it's like mile markers, okay? Right, so we're thinking about the path, we're thinking about net forces, and to make some kind of a calculation, some kind of numerical quantity, we want to think about the segments of the path and two different ways to segment out a path by equal increments of time, you know, like a strobe, right? Or by a meter stick, equal increments of distance. That's like mile markers or meter sticks. All right? Now, let's work out these two ways to partition a trajectory. Now, the trajectory that we're going to work with is a straight down free fall trajectory. We've already done this one, a falling basketball. All right? Now, it's got a vertical trajectory. After 1 second, it's going to fall a certain distance. After 2 seconds, it's going to be a little bit further down. After 3 seconds, even further down than that. All right? So it's falling in a straight line. Okay, so this is a simple path. But if you take strobe, so this is the strobe photo approach. If you take strobe photos, you'll see these 4 positions. You light your strobe at t equals 0 seconds, t equals 1 second, t equals 2 seconds, t equals 3 seconds, and you'll get a strobe photo that looks like this baby. All right? Now, the geometric increment is delta t. All right? So we've segmented this trajectory with time. And we know from last week that the change in the momentum is equal as well. You know, so many kilogram meters per second downward for every second of free fall. Basically, because delta V is 9.8 meters per second more downward speed as long as it's in free fall. Right? So delta P is equal. So delta T is equal, delta P is equal. And that is encoded for us, this geometric quantity. So when I say geometric for time, I'm thinking geometry of space-time, all right? Because time is, so we're thinking about it as a geometric quantity, the way Einstein recommended. And it partners up with the dynamical quantity of momentum. And so that's for the temporal partition of the free fall trajectory. Now, the other way to do your accounting is to take the same trajectory over here and take a photo every 18 meters of drop. So here's, take a snapshot here. Take a snapshot. Y equals minus 36 meters. So this is no longer on a, what do you call it, a basketball court. This is like over the edge of a cliff, 36 meters. That's quite a ways, okay? And then 54 meters down here, another 18 meters, okay? Now that's a spatial partition. And the geometric quantity is delta Y, right? Delta Y equals minus 18 meters. Delta Y is parallel to the trajectory. And of course, the gravitational force is also parallel to the trajectory. Okay, so this is a spatial partition. All right? And here's the question that we're going to think about, that I want you to think about today. And it is simply this. Is there a dynamical quantity that has equal increments? Because remember, delta P, over there on the temporal partition, delta P comes in equal increments. And it's nice. Works out great. Do we have some other kind of dynamical quantity that comes in equal increments for this spatial partition over here? So do we, in other words, is there some delta U? Is there some U, some quantity U that we don't, U for unknown at the present time, that if you partition up the free fall of the basketball in equal delta Y's, minus 18, minus 36, minus 54, and then you compute U, whatever it is, and it comes out in equal sized bytes, what is that? And it works out that this dynamical quantity that should partner up with spatial partitions, the way that momentum partners up with temporal partitions, is called energy, kinetic energy. So here's the formula for kinetic energy. This is the dynamical quantity that if you compute it, every 18 meters of drop, for instance, you'll see that you get equal bindles of kinetic energy change. And if it's on the way down, you're getting more kinetic energy. You're getting more momentum on the other partition, but that's every second of free fall. But if you go every 18 meters, and you could go every 1 meter if you want, but 18 meters is nice and big. This is the stuff where you get equal partitions, equal bite-sized chunks, kinetic energy. Now the formula for that is F delta X, or in this case delta Y, equals delta kinetic energy. And here's the formula for kinetic energy. And believe it or not, this is the one formula that I've always remembered even when I was out of school for a number of years and, not working in physics, but I was always thinking about it. I could always remember this one, 1/2 mv squared for the kinetic energy. And the way that you compute it is by calculating the net force parallel to the path times the increment of path, delta x, or if it's free fall, delta y. And so let's do a couple easy examples of kinetic energy. All right. The metric, and by the way, the quantity F delta x is known as the work. F delta t is known as the impulse. F delta x is known as the work. All right. The metric unit of work is called the joule, and it's equal to 1 kilogram meter squared per second squared. So let's calculate it out. Okay, let's take a 1 kilogram object moving at 1 meter per second. Okay, 1/2 mv squared is 0.5 in parentheses, and then 1.0 kilograms. This is like a liter bottle of water. And it's moving at 1.0 meters per second. Now you got to square that. Okay, now the square of 1 is just 1. All right? So it's equal to 0.5 times 1 times 1. All right? And so that's why the numeric part here is 0.5. But now look at the units, the metric unit of measurement. It's a mass, kilograms, times the square of a speed, meters squared per second squared. And hey, you guys, that is slightly different than kilogram meter per second. And that's momentum. This one is kilogram, key slot, kilogram meter squared per second squared. slightly different. And that's known as a joule. And it is the same. Now, let me show you another slide here. In terms of F delta X, a 1 Newton force exerted across 1 meter is a joule. And it's also known as a Newton meter. Now, a joule, 1 kilogram meter squared per second squared, is also the same as 1.00 Newton meters. So joule, kilogram meter squared per second squared, and Newton meter, those three are all the same thing. And the reason I'm bringing that up is because sometimes you want to work in Newton meters so that you can cancel, cancel some forces left and right. Okay, so if you have energy on one side and a force on the other side, like you're working on a stopping distance problem. Oh wait, did I just say stopping distance? Yes. You're working on a stopping problem, stopping distance problem, you might want to cancel newtons left and right. And then you'll be left with meters. Okay? But other times you might want to figure out a speed. And then you might want to cancel kilograms left and right and be left with meters squared per second squared. Like what we just did with the photon and the retinal molecule, figuring out a speed. You can do that with kinetic energy as well and work. So there's a lot of different ways to put these together. So make a note of that. Joule, Newton meter, kilogram meter squared per second squared. Those three are equivalent. Let me pause for questions. Is today Tuesday or Thursday? Tuesday, okay. Questions? Yes?
What are the three equivalent things? Joules?
They're right here. Joule, kilogram meter squared per second squared, and then right over here, Newton meter. Okay? And sometimes you don't just work in joules, everything's copacetic. But sometimes you want to work in kilogram meters squared per second squared so you can cancel some meters or some seconds or something. And sometimes you want to work in Newton meters because you want to cancel meters or newtons or something. So it's just like you got to keep them in your tool belt. All right, now another quantity that's important for us is the idea of potential energy. And let me help you understand what that is. It's pretty technical, but we'll talk in terms of a baseball. As a baseball rises, it loses kinetic energy. So if you have a pop-up or any kind of a fly ball, on the way up to the top of its trajectory, it's losing kinetic energy. It's basically losing kinetic energy to the gravitational field of Earth. All right? But as soon as it gets up there, so if your buddy's on top of the library and you throw a tennis ball to him and he catches it, you've given it just the right amount of kinetic energy to get up to that height. All right? He catches it, and now he just holds it there and looks down at you and thinks, what if I drop this now? Well, if he drops it now, all that position, all that elevation can be converted directly into kinetic energy again on the way down. Right? And that's what potential energy is about. So if we define potential energy as minus F delta X, in other words, the negative of work, or minus F delta Y if you're in free fall, then the potential energy, that defines the potential energy. So at the surface of Earth, minus F delta Y looks like this. Gravitational potential energy equals minus M times G times delta Y. And hey, you guys, make a note. When you're working with potential energy and work and stuff, you got to use negative 9.8 meters per second squared for your G value. All right? Now we're going to You know, before I could say, you know, if you're just doing a drop distance, just use 9.8 and call it good. But now we definitely care about up versus down, speeding up versus slowing down. So definitely we need that minus sign, and we're just going to keep it in there. Now, it's locked up in that symbol, G, all right? But don't forget, all right? Now we got to use a negative 9.8, and we'll go through a calculation of it in just a second. Okay, so then the ballistic, if you define potential energy in that way, then you can define or model the ballistic arc as an exchange of energy. Remember how we modeled the you know, any physical interaction after the interaction of the skateboarders where they exchange momenta left and right? Now we use ballistic arc or any other trajectory and energy to model an exchange of energies. So one way to say it is this: every joule of kinetic energy that you lose, that the baseball loses on the way up, it goes into potential energy. So your buddy at the top floor of the library, or out of the roof of the library, catches it. Now that baseball's got a bunch of potential energy. It ain't moving, but as soon as he lets it go, it'll all convert back on the way back down to the ground. Vice versa, a joule of potential energy lost on the way down, okay, your buddy releases it from the top floor, from the roof of the library, back on the way down. Every joule that he loses, every joule of minus mg delta y that he loses, it goes into kinetic energy. All right, and because that is true, we say that the total energy of a physical system is constant. The total mechanical energy is conserved. Now, remember we talked about conservation of momentum in collisions. This is another conservation law. Conservation of total mechanical energy. So the symbol for total mechanical energy is capital E. So if you consider total mechanical energy to be the sum of however much kinetic you have and however much potential you have at any elevation, you know, the top of the library, you know, third floor, second floor, sidewalk, the sum of those two, kinetic and potential added together at any altitude is going to be the same number, you know, 21.5 joules of total mechanical energy. Now, you might have more potential. If you're up at the top, near the top floor of the library, you'll have more potential and just a little bit of kinetic. But by the time you get down close to the sidewalk, you're going to have mostly kinetic and only a little bit left of potential. And by the time it hits the sidewalk, it's all kinetic. All right? So this particular formula, E equals KE plus GPE, you're going to have some of this in your, we're going to be talking about it in class today for the next 10 minutes, and then some homework with it. All right? And one of the ways that we want to think about that is energy levels in the gravitational field of Earth. All right? So, we did not do a clicker problem. What's that? Yeah, but we did do, I was going to ask you on a clicker. I must have accidentally deleted it. All right. Here, okay, we'll do it verbally. And, all right, here's what we're going to do. Go ahead and write this down. 2-liter bottle of Mountain Dew. And you move it from ground level up to 10 meters elevation. Okay, so that's like the third floor maybe. Okay, so 2-liter bottle of Mountain Dew up to 10 meters elevation. And then you hold it. So you got your buddy up there on the third floor, and you give him this bottle of Mountain Dew, 2 kilograms basically, and he's holding it out the window. Okay? How much kinetic energy does it have? Well, let's figure it out. It's equal to, I can't believe I screwed up this slide. I'll go ahead and write this down. GPE equals, if I had a chalkboard, I'd do it on the chalkboard, but I don't have a chalkboard. GPE equals minus mg delta y, okay? Minus 2 kilograms times, let's see, mg delta y, so minus 2 kilograms times g, negative 9.8 meters per second squared, so put that in parentheses, negative 9.8 meters per second squared. And then delta y is 10 meters. You know, you're rising up to about the 3rd floor, okay? So a 2-liter bottle of Mountain Dew, that's about 2 kilograms, right? So mg delta y is minus mg delta y is minus 2.0 kilograms in parentheses times minus 9.8 meters per second squared, that's g, and then delta y is positive 10 meters. Okay, so what do you get for those when you multiply that out? What's the number you get? Who's got a number? Mg delta y, minus 2 times negative 9.8 times 10.
Why is it minus 2?
Because it's the definition of potential energy is minus mg delta y. It's positive 196. So let's make it, oh. All right. So go ahead and make yourself a table here. You know, like a list of layers or elevations, 10 meters, 8 meters, 6, delta y is 2 meters for each line, all the way down to the floor level. So the 3rd floor of the library is up there at about 10, and I don't know, 4 point something is maybe the 2nd floor, and then the ground floor is y equals 0. Okay? And so now you're you know what? This is not a mistake. It's a question mark. We already worked out the problem. All right, go ahead and click. Go ahead, multiple choice. Click in your answer. Click in the answer that you know is correct. I had it right. I'll give you a freebie today since it was my goof up. So the GPE, so this is minus mg delta y. And we're going to go through the calculation here in a second. Okay, 10 seconds to vote. 10. Now, don't vote for A, come on. I'm giving you, all right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, yeah, so the answer here is 196. Now, here's how you calculate it. Let's do it out. We won't have to do it verbally. Here it is. Here it is laid out nice and neat. Okay, so here's the definition. GPE equals minus mg times delta y. And don't forget, g is going to be a negative 9.8 meters per second squared. All right, so let's plug in the numbers for this problem. All right, there's a minus sign. And then here's the mass, 2.0 kilograms. You know, because, Mountain Dew is basically water. So it's going to be about 2 kilograms. It's a little bit of water, a little water, sugar, and acid, and some artificial flavorings. And a lot of acid, and caffeine, I guess, if it's Mountain Dew. All right, so now here's G, minus 9.8. All right. And then my change in the y coordinate is plus 10. I've risen. I've placed it from ground level up to 10 meters up. Okay, so that works out to 196 kilogram meters squared per second squared. And that, my wonderful students, is the same as 196 Newton meters and 196 joules. Capital J is the symbol for joules. All right? Now, let's go ahead and get back to this table. Here we go. You can now calculate the total mechanical energy at 10 meters. And it's equal to 196. 196 plus 0 is 196. And now you could figure it out at any level. For instance, just before impact, you've got different energy partition. Now you've got all kinetic, 196 joules, 0 potential, you've converted it all to kinetic, but still it's 196 joules total mechanical energy. Matter of fact, go ahead and fill in this table. Once you get total mechanical energy at any level, you can put ditto marks all the way down in that column. 196, 196, 196. Now up here at 9 meters up, you're going to have a lot. You're not going to have 196. You're going to have a little bit less than that. But you're going to have a little bit of kinetic energy, whereas over here at the very top, you had 0 kinetic energy. So you drop down 1 meter, now you're going to have a little bit of kinetic, but you're still going to have most of your potential. And then somewhere at about 5 meters, not somewhere, but exactly 5 meters, you've got 50-50. 98 joules potential, 98 joules kinetic. And then down here, you know, so if I don't have 2 meters, but at 2 meters, I'd have almost no kinetic potential energy and mostly kinetic. So I might be at 2 meters, and you know what? On homework, you're going to figure this out. You'll figure, yay, figuring out kinetic energy, I think, at 4 meters. All right? So let me dismiss, and it's 1:15. Oh, wait a minute, we go to 1:20. But this is a good time to dismiss. Homework 8, you'll have this table concept and maybe some more brain burner stopping distance problems. Okay, I'll see you on Thursday. You're dismissed. Lights. Yes, please.
Are the new office hours on web courses?
I thought I listed them on there. It's 10 to 11.
Okay.
Yeah.
I just want to make sure.
Yeah.
Thank you.
What days are your office hours again?
Wednesday.
Okay, thank you.
10 to 11 on Wednesday. Yeah. Darian, did you hear about the office hours? 10 to 11 on Wednesday. Okay.
Remember, I've already visited you at 7.
Yes, that's right. 10 to 11 on Wednesday. Shanice?
We're still recording.
I know.
Hello. So, okay,
Hello.
I slept up a little last week, and I was wondering if there was any way for me to get a copy of the questions from